Hello and welcome to this code along with the autodidact scientists. We're gonna be building a convolutional neural network for the purpose of classifying images of cats, dogs, and birds. Now the data sets come from Kaggle and a Google API, and I'm going to basically show you how to build a neural network architecture. We're also going to deal with class imbalance, and we're also going to deal with overfitting as well. Now, when we're going through this particular code along, you've got the option to either train the model yourself, and that takes around 20 minutes with in Google Colab with a GPU enabled. But also I'm going to, as you can see here on screen, we're going to download some pre-trained models as well. That's generally a lot faster, but I'm going to give you the code for both, and it's entirely up to you which one you choose to run. For the sake of simplicity, I'm going to be using the trained models. There are a total of 3 convolutional neural networks that we're going to train in this particular code along, and you'll see why as the project comes together. Okay, we might as well get started. And the first thing, and obviously the most important thing, is to import our libraries. So we're importing OS, import shuttle, import random, import zip file, import tar file, import numpy as np, import pandas as pd, import seaborn as sns, import TensorFlow as tf, and import matplotlib.pyplot as t. Okay. What we've imported here, I'll start from the bottom. Matplotlib is a package that we can build charts and plots with. Seaborn is also a package that's built on top of Matplotlib, which also gives us the option to create some charts and scatter plots and whatnot. And it's generally quite easy to use, and I think it looks better than Matplotlib. TensorFlow that's what we're going to use to build our convolutional neural network. Pandas is for data frame manipulation. NumPy for our mathematical computation. Tar file and zip file is to unzip and extract our data as they're stored in zips and tar files. And we've got import random to basically, generate random. We're going to be generating random images with some sort of manipulation on them to increase our data set size. And shuttle and OS for some high level computations that we can do in terms of our library and file and folder structure. Okay, so once you've typed that out, we can run that cell and do the imputations. Now, if you're using Google Colab, all these should be already installed, so you won't get any errors. If you're using it on a personal computer, there may be 1 or 2 things that might not be installed, but you can install them using the pip install and then whatever the package name is. Okay. The next step, we're going to download the data. We've got the images of cats and dogs, which comes from a Google API. It was originally hosted on Kaggle, hence the file name Kaggle cats and dogs. And then we've also got the image of birds as well. And then this part here, we're going to download, and the pre-trained models and the training histories of them particular models. Now, the notebook will be in the comments of this, sorry, the description of this video. So just download it, paste this code into your notebook, and run it, and everything should download, and we should be good to go. It doesn't take too long to do this at all. So, okay, we'll let that download. And for the time being, what we're going to do is combine the data sets. So let's just make this will be these files will be downloading to our session here. So let's make these files into variables so we can extract them and get the images from within them. So okay, so this will be uploading to the dashboard. So it'll be content, and then what's it called? Kaggle, cats and dogs 33667A zip. Okay, and then we want the bird one as well, so we'll call it Caltech birds. That's where it comes from, Caltech, and it's a tar file, and it's the same file location. Content CUB 200 2011 .tar, and I think that should do it. And we're going to create a base directory under the variable base there. Okay, and we'll call that data. Cool. So is everything downloaded? Yep, everything's downloaded. The models, the training histories, and our data there. The sample data is a default for Google Colab, so don't worry about that, but we'll just hide that for the moment. So we'll run that, and we've made our variables. That's cool. Okay, now the next stage is we need to extract our data from these two zip file, the zip file and the tar file. So let's start using the zip file that we imported earlier on. Let's zip file, and we'll cats and dogs zip, and we set that to write as my zip. And basically what we're doing here is just saying extract all into the base directory. Okay, so what we can do with that, we can hold shift and press enter, and that should get to work. Oh no, it hasn't got to work. Have I spelt that wrong? Cats and dogs, content cats and dogs. Have I spelt it wrong? It's just to double check. We can just copy the path, and if we put it there, yeah, I wrote something wrong. So rerun that cell, and we should be good to go. Yeah, it's working now. So that'll extract that, and in the meantime, we'll do the same for the next file, but this is a tar file, and the code is slightly different. Caltech birds. I'll tell you what we'll do. Let's just move that Caltech birds. Yep, that's fine. So tar, and that will also need to be right as my tar. Ooh. Okay, and then my tar extract all into the base directory, and that should do the same thing. There we go. These we're going. Okay, so if we just refresh that, let's have a look. There we go. We should have them in the temp files. I don't want to go a file higher though, but it will be there. Otherwise, it would have edited out. So, okay, what we need to do now is, well, for the cats and dog images, there's no further pre-processing. All the files are stored in their particular classes. and the directories are pet images / cat and pet images / dog. So what we're going to do now is check how many images are available for each category, and we're going to store them into variables. So let's have a look what we can do here. So dogs directory, and we'll use os path.join base directory, and we'll take a look at pet images, dog. Oh, I shouldn't have hit that pretty premature. Out of habit, because we might as well do both in the same. Copy and paste that. Say we're typing it again twice, and then we'll change that to cat. Cool. And then we will print, and we'll use an f string here. There are, and then it's len. So we want to get the length of this directory, and it will be base dogs there for directory, and we'll use the f string there. Images of dogs. And then what we'll do, we'll copy and paste that, and we'll change the bits because we don't like to type the same things wrong. And I've just noticed I've got that wrong there. So there we go. Okay. So if we run this code now, this particular cell, it'll give us a printout of how many images of the dogs there are and how many images of the cats. So we run that, and there we go. It's quite a nice split. 12,501 images of the dogs and 12,500 images of the cats. Okay. So the Bear data set is quite different. Now, the data sets that we have downloaded from Caltech, it's commonly used to classify species of birds. So there's a directory of each species. So what we're going to basically do is treat all the species of bird as a single class. And so what we're going to need to do is move all the bird images to a single directory, which will be pet images / bird. And we will do this with the code in this particular cell. So let's do raw birds directory, and put the file location there. So it's TMP for temp data, and it's cub 200 2011 / images. That's the directory there. So the base birds directory, same as above. What we're going to do is just copy that, put it there, and we'll change that to bird. Okay, and I spelled birds wrong. There we go, birds. That should be fine. Okay, and then we're going to make a directory, which is going to be the base birds directory. There we go. Cool. And now what we're going to do, we're going to need to write a nested for loop to basically move all these images around and extract them from each of the species classes into the pet images / bird directory. So for subdirectory in OS, there we go, there. So all the images in the raw bird directory. Okay. Sub directory path needs to be, we need to join that. So we need to put path.join again, raw bird there, that's already auto completed, and then sub directory is the path. And then we need to do another for loop for the images contained in that subdirectory. So sub the path should be okay. And then what we're going to do is use the shuttle move function. I'm going to use the join sub the path image, and then the OS path join and then it'll be base birds directory, won't it? Okay. And then what we'll do the same as we done up here. We'll print an F string and change it to birds. And we want to do base birds directory. So that'll move all our images around and then print out how many images of birds we have. So let's run that and see what happens. Hopefully you got it all right. Yep, we have. So there's 11,788 images of birds. So that is, it's not greatly unbalanced, but there still is a slight imbalance there. So, we're looking quite good. So what we're going to do now is we're going to take a quick look at some of the images that we're going to be trying to predict. So we're going to use the IPython display, and we're going to import the image and, well, display as of that function. If you're using Colab, IPython should be already installed. Also, if you're using anything like Anaconda, IPython will already be installed as well. If not, you can install it using pip. Right, okay, so we want to print and we'll put the sample of cat images. And so we want to use the display function and we're going to basically select a random image. File name, I'm going to use the F string again. And then, oh no, I need to put the speak marks there. And then OS path join, and we want to take a random image out the base cats directory. Just there. Base cats there, and tell you what, we won't do it randomly. We'll just select first image, and that should be cool. So make sure all my brackets are done. I think that my brackets are fine there. So what we can do, we're going to copy and paste this 3 times, and we're going to change that to dogs. Dog, and we need a line break under that, so we're going to do a no, will we? We'll just have to see. I think it should be fine. Let's just put a double dog images and then bird images, and we'll make the amendments here. So that will be dogs, and that will be dogs. That will be birds, and that will be birds. So if this works, we should see pictures of our animals. So we've got the cat, we've got the dog, and we have the bird. Cool. So what we're going to do, let's just highlight that, and what we'll do is we'll put a text box there, and we'll do the train eval. Okay, so before we're going to train any sort of model, we're going to split our data into training and evaluating sets. So what we're going to do is use the Keras API, which includes functionality to read images from our directories, and what it'll do will basically split the data to create a different directory for each of the splits. So what we have to do, we'll put this together in the code, and this is basically just I'm only using what was written on the documentation. So we need to make a list, and we're going to call it train cats, train dogs, train birds. Oh, I've done that wrong. Yep. So what I'm doing is making a list of the directory names. Okay. And then eval cats for evaluation. Eval dogs and eval birds, and I'll just so that is our list of file directories. Okay. The next step, we need to make a loop, basically a for loop, into train eval directories. If not, OS path exists. So we're checking if it exists already. OS path join base and then there. So it's basically saying if it doesn't exist, make it. My semicolon there, well spotted. Make is OS path join base there directory, and that should give us our folder. So if you run that, have a look. I have to go off one. Where's our base? Where's our base there? Temp. Oh, there we go. Data. There's our evaluation and train, and inside them there should be the birds, the cats, the dogs. There we go. Perfect. It worked. Okay. Now, what we need to do now is actually move our images into these particular directories, and we can do that with a function because we don't want to type in a load of code 3 times. So let's just do a quick function. So move to destination, we'll call it. So it'll take the origin, it'll take the destination, and it will take the percentage split, because we need to, split the data into a training and evaluation set. So it'll need a percentage split. So we'll do norm images equals, so we need to take the number of the images, which will be in that particular directory that it's looking at. And it'll be the origin destination times that by the percentage split. So we get a percentage basically. And then we'll loop through them. Image, so we loop through the image name, the image number in zip, and we're going to zip them for computational purposes as well. Sorted. And I think we need the origin here. And then we need to, and then the range, isn't it? It'll need to be a range number images, and then should be cool. There's a spelling mistake there. Okay, done there. Let's get back to that. And then invoke shuttle again to move them. Dot join origin image name, and then I think it will be destination. I think that's going to work. Should work. Just run it. Let's just apply, get that functional. We'll try it out now. We'll try it out. Okay. So so we'll apply the function, move to destination. We'll call our function, and we'll call it on the base cats there. So that's the origin. We need to put the destination. So that will be the base train cats. Okay, and then we need the percentage as well. So it'll be 0.7, which is 70%. So that should do it, because we've got the origin, we need the destination. We're telling it to put it all there, and then the split. Okay, so let's do that 3 times. Let's change this to dogs. It should be birds, dogs, birds. There we go. I think that should work. Okay, and then what we'll do then, we need to remove what's left in them in the origin folder. into the evaluation folders. So let's do that again. So we might as well just copy and paste, and we'll write a little note there, move remainder into evaluation folder. Okay, so the code will be the same, except we need to change these to eval. And as we are making, we're putting the remainder in. So we want whatever's left in there. So we change that to 1, which will indicate 100% of whatever's remaining. So let's just give that a blast. And it's complete. Okay. Okay. So let's just take a look at what we've got. There's our train. Birds, cats, dogs. We won't be able to see the images in there, but that's fine. They should be in there. Fingers crossed. Okay. So now, if you are doing this on your local machine, you go and take a look at some of those images that are stored. You might notice that some of the images are corrupted and have 0 bytes. And also, the cats and dogs zip file included a database file for each class that needs to be deleted. So if you go now to train a model, it'll cause an error because 0 byte images aren't valid, and .db files aren't valid images as well. So it's good practice to always make sure that you're submitting files with the correct specifications to the training algorithm before you actually start it. So how are we going to fix them? Let's run some lovely bash commands. So I'm going to put find in the temp, we'll put temp data, and we're going to look for images that are 0 in size, and we're going to execute a remove function on them. And then also find temp. We're going to do the same for well, it's going to be type then, isn't it? It's going to be type name. Anything that isn't a JPEG .jpeg, let's delete it. That's what we want to do, isn't it? That's a good way of doing it. And that should be good to go. Yeah, so that removes anything with a 0 size, and this removes anything other than JPEGs. So hit the go button, and that ran fine. I haven't done bash for a while, so there we go. Okay, now let's see how many images we have. And what we can do, instead of typing the whole thing again, let's just steal this. And what we'll do, we'll paste it there. But let's just paste another one there. We need 6 different ones because we're going to check in 6 different files and folders. Okay, so what do we need to see? We need to see our, if we go to the base, let's go to the base there first. I'll tell you what, I might as well delete them. I'll just do it one by one. Write the first one first. Base there, and we need to see the contents of the train cats folder, and we'll put there are images of cats for training. Okay, and that we should be good there. We should be good. Why have I given it error? Oh yes, that's why. You need to do the join. Okay, and then we need to close that bracket, and I think we'll be all good on the brackets there. So the len list there. Okay. What have we got? I'm sure that'll be fine. Why is there an error? What's this? Is it that space there? Oh, we'll just give it a blast and see what it says. Okay. And then we'll do the same for dogs. Okay. And then same for same for birds. Birds. So just run that. Will give me an error? Invalid syntax. There's something wrong here. What am I doing wrong? Got the list there, yeah. The OS path join base there. Not really sure what's going on. Let's just. Okay. What the hell did they do there? I have no idea what I've just done there. Never mind. Just paste it over here. Paste it over here. Ah, that's why. It's okay, so let's change that. Okay. Dogs. Birds. Never mind. Dogs. Birds. And then let's do it one more time. And what we'll do is look in the evaluation. So we can take that, replace that, and we'll put evaluation. There we go. I have to copy the whole thing. Okay. Okay. And we should be good to go. So that should give us the contents. There we go. Bingo. So it turns out, like if you look at the numbers here, that there wasn't many files that shouldn't have been there. So we're quite we're quite good. So let's just move on. We're good to go. So I'll tell you what we'll do. Let's create because we've got a lot of balanced images there, let's create an imbalanced data set so we can train a model on that also. So let's just call this create imbalanced data set. Okay. Right. So what we'll do, how are we going to do this? We'll do a for loop first. So train eval there. So we will, if not, os.path exists. So if it doesn't exist, we'll join base there, and we want to create imbalanced, but we need to put that in quotes, and then be like that, and then we need to put the there. So that there is that'll be called like imbalanced cats, imbalanced dogs, what and whatnot. So we need to put a semicolon there, and then we'll make directory directories os path. We'll join base there will be then, if it doesn't exist, make it, basically, is what we're saying here. Hit that. Exists, that's why. Bingo. Happy days. Okay. So we're going to have to do this part quite similarly. Can't even say that word. So let's create a function first. Copy with limits, because we don't want to copy everything. And it will take the origin, it will take the destination, and the percentage split again. And okay, so let's just copy. I think we should be using, it should be the same thing, but we need to make a copy rather than, so just fix this. Okay, so we don't want it to move, we want it to copy. To be there. Okay, is there anything I need to change there? Percentage split, that's fine. Zip, sorted, cool. Same, but we need to copy. We don't need to move, we need to copy, and that's the key part of that. Okay, fine. Let's do that function. Bingo. Cool. Now we have to basically apply the same code here, but we're going to change it to copy with limit here. So copy with limit. And let's do that for there. Let's do it for there. Do it for there. I pressed C instead. Okay, so I have to recopy that. Got a new keyboard, you see, and I'm not quite used to it. So I'm making all sorts of nonsense mistakes. Bear with me. That's just the way it goes. Okay. And we have to change. What do we have to change? We need to change this part, don't we? Because we don't want to copy it out of there. We want to copy it off the base directory. Okay, so let's get rid of that. Get rid of that. Let's get rid of that. Okay. So then we will have to define here train hats. Okay. And we need to change that to imbalanced train cats. And we will let it take 100%, copy 100%, remember? Okay, so let's copy this. Let's copy it to there, because I'll show you the difference what we're going to do. And that should be fine. We'll just make our amendments. So let's call it dogs. Train dogs, and then birds, and train birds. Okay. So we want 100. Let's just call that 2, and let's just call that 1. So we're getting 10%, 2%, 100% copied over. Right. That's for the train. Let's do the same for the evaluation. So let's do our amendments. Eval. We'll keep these numbers the same. We need to do eval there. And that should do the same for the evaluation. Okay. I think we're good. And then what we'll do, we need to print. Let's print them again. Let us know how much there is. Let's just delete that. We don't need that now. So we will have to change this to add imbalanced. Change, just add that there. Add that there, add that there, that there, that there. Are we good? Imbalanced? Oh, I haven't spelled imbalance right. Okay. I think that'll go. Let's just, if in doubt, code it out. Let's go. Oh no, copy limit takes 3 positions before we're given. Have I missed something there? Percentage split. Copy with images. That shouldn't be. Okay, base there. Ah, that's why. I forgot me bloody brackets. That is why. So that, because that is the first element. There we go. Just goes to show you can never be too careful. And that means I'll have to shut them again. Base there, base there. So, okay. Well, that's fine. That's right. That's cool. Okay. We should be good. Let's give it a go. Try it again. Boom. Oh, invalid syntax. I'm missing the end bracket. Never learn, do I? Okay, so we've got the copy with limit base, and then that is there. Okay, we need. That's why I'm so silly. I'm so silly. I need to put it path there because it won't know what it's doing, will it? Here we go. Is that better? There we go. Should be better. Just copy that. If in doubt, code it out. Okay, so yeah, because we need to, done. That should be fine. Happy days. It's running. Cool. So let's just let that run. It's making the copies and put them into the folder, so it can take a bit of time, but there we go. So now we can see that we've created a very imbalanced data set to test as well. So happy days. Okay. So what the next stage is, let's just create a, let's call this selecting a model. Okay. So we're going to create a model architecture, and we're also going to define a loss function, an optimizer, and some performance metrics. And we will leverage the Keras API, which I mentioned earlier. So we've already imported TensorFlow. So TensorFlow.keras, let's import, we need layers, models, and the optimizers. Cool. And we will create a function, and it will be called create model, because that's what it will do. It will create a model. It doesn't need anything in there. Okay. So let's make let's, should we put some doc strings? No, well, let's just do a comment for now. Simple CNN structure. Oh, the model is from the model sequential, we'll call it. Yep, sequential. And we will create, why is it doing that? Come here. Okay. So we want a layer, and we want a convolutionary layer, which is conv2d, and we'll put 32, 3, 3. We'll put an activation function on this layer, relu, and the input shape will be the size of our images, 150, 150, and 3 color channels. Okay. And the next part, we will need a max pooling layer, and that might be somewhere where you can experiment. It might be worth, put that wrong, layers. It might be worth using average pooling, for example, but I'll leave that up to you. But for the time being, we're going to use max pooling. So we need to set that as 2. Cool. Okay. We'll add another convolutional layer. Conv2d. And that this time 64 neurons, 62. Why did I say 64? There we go. One of my favorite numbers. Okay, and we'll have the activation as relu, right? And what we can do, we can just copy this max pooling layer. That should be cool. So if you put a comma there, we'll have that. We'll take another convolutionally, leave that at 64. We'll put another max pooling layer. And then we'll do another convolutional layer. But we'll change that to 128 neurons. We'll put one more max pooling layer. And then we will flatten. I think that should be good enough. layers, rather dense layer, 512. Activation on that one will also be ReLU, and then we'll do another dense layer for the output, and that will be 3. There's 3 classes, and the activation will be softmax. And that should do it for our simple convolutional neural network. Convolutional neural network. Okay, right. Happy days. So from that, let's then compile the model. Model using the model compile. Forward. Okay. Let's set the loss. Keras losses, isn't it? I can't remember. And we'll use the sparse categorical cross entropy. Okay. The optimizer will be optimizers, and we'll use Adam. Use Adam. And then the metrics we need. I have to put on a list. Keras metrics. Sparse categorical accuracy. And then what we need to do is then return model. Okay. Right, that should be okay. Let's give that a blast. Invalid syntax. What have we got wrong there? I got something wrong. Keras metric sparse categorical accuracy. Comma. It was a comma. There we go. Done. Okay. Right. So let's print out a model summary, and what we'll do, let's go for the imbalanced data set first. So imbalanced model equals our function create model, right? Happy days. And then we'll print, for God's sake, print imbalanced model summary, and see what happens. And what we'll have, oh, for God's sake, model, create model, yeah, balanced model. Oh, we're balanced. That's why. Come on. There we go. So there we go. We've got the layers, the parameters. Yep, cool. Total parameters, trainable parameters is good. Fine. Cool. Okay. So we need to train the model, and we're going to use the Keras image data generator. And that has built-in functionalities, so we can easily feed our model with raw, rescaled, or augmented image data. And another interesting functionality within the image data generator is the flow from directory method, and that allows us to read the images as needed from a root directory. The following arguments: directory, target size, the batch size, and the class model. You know, they'll give us a good hand in training this imbalanced data set. So let's just code it out. What I'll do as well, I'll provide links in the the description of this video to the Keras image data generator tutorial, which is quite handy if any of this goes over your head. Okay, so let's import. Let's get coding. So from TensorFlow Keras pre-processing, it's stored in, isn't it? Yes, it is pre-processing. Image import image data. It knows Google Colab knows. So okay, So for the time being, let's just normalize the images. So train data gen, we'll call it that because we're using the data image generator. The image data generator, so they're completely backwards. So image data generator, that is a mouthful. We're going to rescale them. We're just going to change them to 255. And let's do it for the test data gen as well. Image data generator definitely could be a song equals 1, and I'll do the same. Happy days. And then we'll the train generator, and it'll be, look, that will be the train data gen. And we'll use the flow from directory method. And what we're basically doing here is pointing it to the imbalanced directory. And if I remember correctly, that should be temp data imbalanced train. Yeah, I think that's it. Target size, we want to make the target size is the same as the model we built. So that will be 150 by 150. The batch size for the model we would like to have 32, and the class mode is binary. Okay. So that the binary part here is how the labels are represented. Binary is used to indicate that the labels will be 1D. So, and that's basically done for compatibility with the loss and evaluation metrics when we compile the model. It's not actually indicating it's a binary classification problem. Okay. It's the same for the validation. So we need to put the test data in this one. And it's the same thing, so I can pretty much copy that flow from directory, but we need to change that to our evaluation folder. Same. Cool. We need to put the bracket there, but let's just just because it looks like the one from the top. Happy days. There we go. Great. Let's get rid of that. Okay. So let's just do a quick inspection of both generators, the training and validation, and make sure that they use the same labels. So we will need to print an F string again. Labels for each class in the train generator are, and then it'll be train generator class indices. Yeah, that's right. I remember that well. I haven't used this for a while, you see. Okay. I think that should be it. And let's just copy that. Well, let's spell labels correctly first. Copy that. And we'll put the validation generator. Validation. And that should give us it, shouldn't it? Yeah. Birds, cats, dogs. Birds, cats, dogs. Happy days. So that's our binary class. Well, not the binary, it's our numerical representation. 0 is birds, cats is 1, dogs is 2. Cool. So, okay, let's train a convolutional neural network with class imbalanced data. Okay, so let's load. First of all, I'm going to, as I said earlier on, I'm going to be using the loaded models because otherwise the video will be 10 hours long and no one's got time for that. Okay, so here I'm going to load the pre-trained models and their histories. So it's imbalanced call it imbalanced history. So that's all your training history. And we save that. We downloaded it. So let me just double check where that will be. Content. Okay, so it'll be model imbalanced, history imbalanced. That's the one I want. And we want that. So let's just copy that path. Is that right? Yes. And then let's just surround that in quotations. And then we'll do the same. We want the model. In fact, I shouldn't have really copied that because I don't even need that. So Keras models, and then we need to use load model. And it will be model balanced. I don't think. Yes. Okay. That should be fine. Let's give that a blast. There we go. Yes. Yes. Happy days. Okay, so this next code, I'm going to start with these because only run this if you want to do the training yourself. Take about 20 minutes to half an hour with a GPU. So run only if you want to train model yourself. 20 to 30 or to 30 minutes with GPU. Okay, so it would be balanced history equals imbalanced model fit. And it fits to the train Jenny Ray core. I've done that. It fits to the train generator steps per epoch, isn't it? Steps per epoch, I think. We'll see. And then epochs 50. Your validation data will be the validation generator. And then your validation steps, let's say, 80. So let's just comment that out. So you only need to run that if you want to do it yourself. But we're not going to do that. We're going to save some time. Okay. So first of all, we need to analyze model performance properly. So it's important to track different metrics such as accuracy and loss function along the training process. So we're going to define a helper function to handle the metrics through the training history, and that this function will work for both the loaded model and for if you want to train your own model. So okay, let's call it get training metrics and take the history from the model. So we need to make sure say whether whether or not you've trained the model yourself or you've used the preloaded. So what will that be? That will be if not is instance. If not is instance, is that's the one, isn't it? Yeah, because that's a method. And then history the pandas core frame data frame history equals history dot history. Sounds strange, but that is correct. So you see history is the sparse categorical accuracy. Okay. The val accuracy is history. Can't spell at all. And that is the val sparse categorical accuracy. And then our loss history. Come on, it's doing my head. I'm typing that now. Loss. And the val loss equals history. Val loss again. Okay. And then we need it to return. Oh, here we go. Spelling history wrong again. Swear. The val accuracy, the val accuracy, the loss, and the val loss 2. Okay. So that should be fine. Let's just run that. Yep, that should be fine. Cool. Okay, now we need to be able to plot the metrics and losses for each training epoch as the training progresses. So let's create a function to do that. So we'll plot the train eval, and we need history as an input, and it'll take the accuracy, the val accuracy, the loss, and the val loss. We get training metrics looking at the history. So we'll do the accuracy plot. I hate doing plots, but they have to be done. So it'll be in a data frame format, won't it? So it'll be, okay, we need to put training accuracy as a label. And we're building a dictionary for this. So that will be ACC. Oh, I don't need to put it there, accuracy. And that will be the val. Cool. Okay. And we'll put the Seaborn line plot. The data will be the GC plot from above. Happy days. Oh, plot. Yeah, that's right. Plot, and we need to set title, isn't it, with Seaborn training versus eval. See, I've just spotted that as well. Get rid of that. And then we need to put the, is it set? Yeah, it's set, isn't it? Set label. We'll call the X as the, it will be the epochs, won't it? And then the plot set by label, and that will be the sparse categorical. See, happy days. And then, oh, actually, yeah, PLT, we'll show it there, PLT show. And then we will create a new line. So let's just print a little something there. And then we'll do the loss plot. So we'll just do the same thing. We'll just copy that. Soddy. And we'll call it loss. Do that. Over then. So we need to change that to loss. Evaluation loss. And the evaluation loss there. Change that to loss. And that to loss. And also we need to use that to loss as well. And I think that should be it. Cool. Okay. Cool. And then plot train eval advanced history. So this will just, yeah, cool. Okay. There we go. So this is pulling the training accuracy from the loaded models, the ones that we've already, we've downloaded and loaded. Okay. So, I mean, you can see from these two plots, it's, the models are overfitting the training data. The evaluation accuracy is still pretty high. So what does that suggest? Does it suggest that the imbalance isn't such a big issue after all, or is it too good to be true? So we'll take a look. We'll dive a little deeper. We'll compute some additional metrics, and that will allow us to, basically explore whether the class imbalance is hampering the model. Okay, so we're going to compare the accuracy score, a balanced accuracy score, and we're going to use a confusion matrix as well. So let's get cracking. Okay, so we're going to need the scikit-learn metrics, and we're going to import a confusion matrix. The confusion matrix display, I think that's what it's called. The accuracy score, and the balanced accuracy score. Okay, just run that. No, what is it? Confusion matrix. Oh, I spelt it wrong. That's why. Tell you what. Okay. So what we're going to use here is the validation generator. And we're not going to shuffle what's in there because that will allow us to compute the additional metrics a lot easier. So if we put val gen, and we'll call it no shuffle. Okay. And we'll take the test data gen from earlier and the flow from directory. So we're just doing similar to what we've done before. And I'm just going to copy and paste it. Is it too far away? There it is. Let's just take that. But it's going to, I'm going to have to change that, aren't I? It's going to be eval. Okay. Target size is the same, 150, 150. Batch size, we're going to have to do 32 as before, and the class mode again, binary. And because it's not being shuffled, we'll call shuffle false. Okay, run that. Valid syntax, that's because me comma again. There we go. Happy days. So we're going to store all the true values in a variable, and we'll use the no shuffle classes. Easy enough. And then we're going to use the model that we downloaded to make the predictions. And we'll store that there in balanced. Predictions in balanced. And it's the imbalanced model predict. And it'll predict on the val gen no shuffle. And then we will get the predictions. Let's just get that. So what we need to do is get we're going to get the argmax only because we're using the softmax output. So it'll be predictions imbalance, won't it? So it'll be the one above and axis to be 1. Cool. Predictions imbalanced. It's not my day for spelling today. Okay, so we need to print the accuracy score, and we'll use an F string again. Score. It will be the accuracy score from scikit-learn, and it'll be the true labels versus the predicted labels. Balanced. Okay. And then we'll do the same for balanced accuracy scores. Just same sort of thing. Just choose that function from scikit-learn as well. I think that should do it. So let's go. A little bit of time just to run. So 2 minutes. So I'll just pause. What I'll do, I'll pause the recording and we'll get cracking when it's done. Okay, we're back. And we've, comparing the accuracy and balanced accuracy metrics, we can see that the class imbalance is starting to become quite apparent. So what we're going to do is now compute a confusion matrix of the predictions. So let's just get cracking with that. So let's just make a new function for the imbalanced confusion matrix. So it'll be confusion matrix, and again it'll be the true labels and the predicted labels, imbalanced data set, and then confusion matrix display. We will put the imbalanced CM. So display. We need to display the labels, isn't it? Display labels, I think. It's not just display. Yeah, labels. So bird, cat, and dog. Birds, cats, dogs. Birds, cats, dogs. And then we use the plot values format, and we'll put that as T. What are we going to get with that? Cool. We'll code the next part here. So it seems that it's also, the imbalance is also in the evaluation set. So what we can see that there's an overwhelming majority for cats. And that is basically just due to the sheer weight of the amount of cat images in there. So it is skewing the model. So we need to calculate the proportion of the misclassified birds, cats, and dogs. So we can calculate that and just see how bad the model is doing at the moment. So let's make a few functions. Well, not functions. Let's make a few calculations rather. Classify birds. We'll do the birds first. So how are we going to do that? That will be, we need to see the imbalanced CM, and they are in the tuple. Is it? It's like a list. Yeah. Okay. We need to add them. So what we're basically doing here is adding. We're just calculating the misclassifications, so the true positives and how many, the true negatives and the true positives, and calculating basically the precision. And that will then give us a percentage of how many have been misidentified by the model. So we need the CM again. So let's take, so it's position 2 again. Cool. And then we will divide that by the total imbalance axis is 0, okay, and that will be 0 as well. So that'll give us the misclassified birds. Do it for the dogs, the cats and dogs as well. So yeah, all we're doing is calculating the precision. Okay, and it's 2. And that'll be 2, 1, won't it? And that will be 1, 2. And then the class will be 1, 2. Birds are 0. Yeah, cool. Okay, we've got the calculations, so let's print them. And again, let's use a f string. Proportion. Oh yeah, there we go. Proportion. Brain fat then. Classified birds. And that will be miss. Classified birds, and we'll set. We need to do a times 100, and we need to format it. Right, format it as a percentage then, shouldn't it? Yes, that should do it. So if you do the same, cats and dogs, just all the corrections. So it will be cats and dogs. Okay. Cats, dogs. Okay. There we go. So we can see that it is causing quite a problem. And if you went solely on the accuracy of the model, you'd think your model is performing better than it is. So we need to, this is why we need to rely on several different metrics, and that will then do a better job of capturing these kinds of issues. The standard accuracy of our current model is completely misleading, and it provides a false sense of security. So let's prove that point a little bit more. Okay. So let's predict a model. Let's make a model that only predicts cats. Okay. Just build that. Ones, and we'll see why that isn't. Why this is, this will make it more obvious, shall we say? Let's and then print. We'll do the accuracy score here. Score. Accuracy score, and then what will it be? It'll be Y, the true labels, and then all cats. Okay, I should give it a Y true accuracy score, all cats, and then let's print the balanced accuracy of that as well. Okay, all cats. Let's go. Y true, so it should be Y true. There we go. String expecting Y. It has got that. What have I done wrong here? Where are we? Y. That's right. Here we go. Always forget a brackets or a comma. There we go. So if even it was just looking at cats, and it's got because the cats are the majority class, so even still it's getting a 77% accuracy, and the balanced is a third, only because it's a third of the classes. So what can we do to deal with class imbalances? There's a number of techniques. Probably the most popular is something called SMOTE, and that basically synthetically oversamples the minority classes. We won't do that at the moment because it does take quite a while, and that is, it's beyond the scope of what I want to do at the time for the time being. We will probably have another code along with how to use Smote, and that will be covered by either me or Salman. Okay, so we've just computed metrics with a class imbalance both on the training and evaluation sets. So what we need to do now is we'll run through how the model performs with a class imbalance only on the training set, and not the evaluation set. So let's get coding. So again, let's do the no shuffle. But what we'll do, we'll just copy it. There we go. We'll just copy that. That's all we need. And this is just to demonstrate how it performs. The imbalances is only on the training set, which is quite, sometimes it happens. Sometimes that can happen. If you use a random split, it's possible. So let's just do it'll be data eval then, isn't it? Because this will be the evaluation set is not, this particular evaluation set is not imbalanced. Shuffle false, fine. Okay, so we'll just do it in one code. So again, let's do where are we? We can just copy it. There we go. This is what we need. Lazy. Just check that. Y true is no gen shuffle classes yet, because it's calling that. And we'll just call it, we'll use the imbalance model. That's fine. We don't have to change anything there. Okay, that's fine. Instead of that though, let's do the confusion matrix instead. Confusion matrix, the Y true, Y pred, same again. Oops. So let's just have that run, and I'll pause the recording and we'll come back to it in a moment. Okay, we're back again, and as you can see, it's still quite skewed, but not as bad as the previous attempt. So okay, that's good to know. What are we going to do next? The next part is to let's train with the complete data set, the balanced data set. So we'll call this before then, train with the complete data set. Okay. So in general, having more data is better for models. Having a balanced data set is better for models. So let's create a balanced model, and we will invoke our create model, which we defined before, which is the convolutional neural network. Okay, let's do that. And what we will do, again, we will follow the same steps as before. So train, data gen, image, data rator, and we're going to rescale them again. And it was 1.25. Yes, it was, wasn't it? Okay, so we can copy that. Let's hit it again, but we'll call this one test. Cool. There we go. And now let's point the generators to the complete data set. So chain generator. And it'll be the train data gen flow from frame directory we want. Flow from directory. And we want P data, and it's the full data set, so it'll be train. Target size is, again, same as within the model, 150 by 150. We want the batch size to be 32. 32 is just a very standard issue, default sort of batch size. That can be experimented with. But studies have shown batch size of about 32 are absolutely fine. More brackets, I don't know why I put brackets there. There we go. So let's copy that, and we'll do the same for the test generator. Change that to test, and it will be the eval. Use here. We should be good to go. So let's just give that a blast, and we should run without problem. Yeah, there we go. So we've got 25,750 images belonging to our training data and 11,000 images, or just over, to our evaluation set. So, okay, let's load the balanced history and model. So PDF read CSV, and it will be in the history, same as before, won't it? But it's just slightly different. History balanced dot CSV, balanced model. The spelling strikes again. Balanced history. Balanced model will be, we need to load it through Keras again. Models, load model. It will be the model. Run that. Okay. So what we're going to do now is check the accuracy, and we're going to take a look at this accuracy versus the balanced accuracy. Okay. So let's do it. Algen, no shuffle, and that will be the test data gen flow from directory, and we'll be using the temp data table. Let's just copy that, isn't it? Let's just copy that. Data eval target size. Yeah. But the only thing I need to add is the shuffle being false. Okay, hit it. We've got it. Okay, so now we're going to build where we can have the model predict, basically. So let's get the true labels again, and that'll be from the val gen no shuffle classes. So they're your true classes, and then the predictions balanced model predict, and we want to predict on the val gen no shuffle. And we need to again get the argmax, but it's balanced, isn't it? Balanced, and that will be np argmax predictions. Oops, predictions balanced. Just one, happy days, and then we'll print the max score, and that will be in the form of the accuracy score from scikit-learn, and it'll be y true against the y pred balanced. Okay. And then I need to close the curly brackets, and we'll copy that again. We'll give, because we need to do the balance score again. score, score, and that should be good to go. Might take a couple of minutes, so I might have to pause again. Yep, I will. So we'll pause this, and when we're back, we'll take a look. Okay, we're back and done. And as you can see, both the accuracy score and the balanced accuracy are very similar. But if you're like me, I'm more visual. So let's create a confusion matrix with our new balanced predictions. So it's I need the y true and the y balanced. Cool. We'll run that and we'll take a look. Oh no, we won't because I haven't put display. So let's just confusion matrix display, and we'll balanced CM display labels. We got that right last time, and we wanted the birds, cats, and we'll plot them. Right, there we go. It looks much better because down here are the ones it's classing correctly, and as you can see, the accuracy is quite high because there's very few it's misclassifying in the dark squares. Cool. Let's now then take a look at the training versus the evaluation accuracy and the training versus evaluation loss. And if you remember, we've already created a function for that, which is plot train eval. And all we have to do now is set it to the balanced history. Boom. There we go. This looks much better compared to the imbalanced case. But as we can see on the loss, there's still some overfitting present. Now, can you think of any ways to address the issue? If you are familiar with convolutional neural networks, you could add a dropout layer. That would hopefully, well, it probably would help with the overfitting in a task such as this. However, we can take a more data-centric approach as well to see if we can possibly mitigate the overfitting. Adding a dropout layer is probably very easy, but it's not always the answer. Another possible solution is to keep our model architecture the same, but maybe collect more data, or maybe augment existing data. So let's give that a go. Let's use training data with some data augmentations. So let us just add a new heading. Training with augmentation. Augment data. Here we go. Okay. So what we're going to do is take some of the images that we already have and create new versions of the images. And we'll do that by applying geometric transformations. Now, the geometric transformations can vary. You can zooming in, zooming out, rotating, flipping the images, skewing the images. And by doing this, we basically get a training data set that exposes the model to a wider variety of images within a particular class. This helps in further exploring the feature space and hence reducing the chances of the model overfitting. I mean, it's a very natural sort of idea since doing slight changes to an image will result in an equally valid image. So like, a cat on its side or rotated is still a cat, isn't it? So let's crack on. Let's do it. So we'll call this version augmented model, and we'll call our create model again. Cool. Do it. Now we're going to use the image data generator again, but this time we're actually going to apply some image augmentation. So let's take our train data gen set, and we'll call it image data generator. We'll call the image data generator under a variable train data gen. And what we'll do, we'll rescale because we have to do that anyway. That's 225. And what we'll do here, we'll rotation range, is it? I think that's what it is, by if memory serves. Width shift range, and we'll set that to 0.15. Let's get that out of my way. Okay. Height shift range, we'll do that as 15 as well. And then we'll do the shear range. And I'm just pulling all these out of the documentation I've got on the other screen. Zoom range. Yeah, we'll do that too. And shall we give it some horizontal flip? Yeah, we'll give it a go. As I said, an upside down cat is still a cat. So let's do that. On the test data, though, we won't do any augmentation. The augmentation is only for the training data. We don't really need to we don't need to classify augmented data. We're just training the model on to see if it improves it. So we'll just have to rescale these. Nice and simple. We'll scale it the same way we did before. Happy days. Long. There we go. Cool. Okay. Let's point it to the full data set. We'll just copy it. We'll just copy it. What am I doing? Typing it again. If you can copy it, copy it. Oh, let's get that down here. Let's just double check that's right. And I'll tell you what, let's just call that the validation. Yeah. Eval, yeah, that should be cool. So let's just run this. Yep, same full data. Now, if you'll notice here, there's only a few more parameters. Again, I will leave the documentation within the description of this video, and there are plenty more you can try. These are just a handful that I picked. That's cool. Okay. So, what have we done? We've created some augmentations on our training data. So what does that look like? What do the transformations look like? So what we'll do is we'll take a random sample, the augmented data, and we will import the we need to do the image to array, and we need to do array to image, and load image, of course. So we have to make a function, display transformations, and it will take the generator. So train birds directory. That is, remember, temp data train birds. Okay, and then we need to take a random index, and that's when we use the random and rand int. and it's from 0 to the length of our directory. So that will be OS list there. Train birds directory. Cool. We'll take a sample image, and that will be, we'll use the load image. We will have to use a F string, I think. Just try it. OS path. If it's not, we'll change it, but there we go. And we need to join the train birds directory. OS list there with the train birds. Oh, wow. Underscore button not working. There. And then we'll shut that on. We need to do a random. We need to put the random index here because this will be what is getting sampled. That's okay. And then I need to close my bracket, close that. I think that should mean my bracket's right. And let's just bring this down because I need to put a comma there. So let's just bring that to here. And then I think I need the target, don't I? The target size. And that will have to be the 150, 150. And I think that should do that part. And I think then, what do we need to do? Sample array, don't we? Image to array, and we'll take the sample image. Yep, that's cool. Oh, I've ran it too early. Oops. Just the force of habit, that. And then the sample array will then be sample array, and it will be none to that, I think. Okay, and then we need to iterate then with a sample array. Okay, so iteration array in zip range will be 4. Let's just put it 4, and gen flow sample array size, we want that to be 1, I think. And then array to the MP, you need to squeeze that. Have a good squeeze. Squeeze the array, and then the image needs to be array to image. It'll take the array. Oh, I've hit it again too early. Habit, and then print. And it will be the. Let's take a look at the transformation number, and that will be the iteration, won't it? Iteration. Cool. Let's just delete that. I will refab that. And then we need to display that image. Okay. So if we then let's just take this. Let's just take this, and we'll just call it a sample gen. Okay, so that now, if I put display transformation, is it transformations? Yeah, and I just put in the sample gen there. What it should do is create some data transformations and display them so we can see exactly what it's done. So fingers crossed that works. No, it doesn't. Sample image is not defined. Where's that? Sample image. Sample. Spelling mistake. There we go. So it's taken these birds, picture of a bird, and it's made all these various different skews and flips and whatnot. So there we go. Let's try that again, but we'll make it a bit more extreme, shall we? So if we just take that and put it here, let's make that 90. Let's do that 50. Let's do that 50. Shear range 7, zoom range 3. And then let's just try that. Boom. See, there we go. It's done all sorts. It's done all sorts. I mean, feel free to try a few of your own. But okay, we can do some data augmentation on our data set, and hopefully reduce the overfitting of our model. So let's load the model, or if you're doing it yourself, you're training the model. I'm loading the augmented ones. The augmented history, and then it's history augmented.csv. Okay, and then we need to load the augmented model, and that will be keras models.load model, and it will be called the model augmented. Cool. Let's load that. There we go. Loaded happy. Now, if you want to train it yourself, as I just mentioned, let's just type this out. Augmented history equals augmented model fit, and then it'll be train generator steps epoch equals 100, epochs 80, same as before, I think, and then validation data, okay, and then the validation steps is easy. So I'll comment that is what, if you want to train your own model, just use that. Otherwise, we'll just use our plot. Because we can jump straight to the plot, because we know augmented. Let me just type this out before I start talking again. We know the class imbalance isn't an issue, so there's no need to check for more in-depth metrics. So let's just plot the training history. There we go. Now, if you can see it there. Now, the evaluation accuracy follows more closely to the training one, and this basically indicates that there's no longer any overfitting, and that is quite a good result just from augmenting the data set. As I mentioned earlier, you could use dropout and get the same thing, but sometimes, from rather than looking from a model-centric outlook, it helps to look at a data-centric output as well, because at the end of the day, 9 times out of 10, you're only as good as the data you've got, and you could absolutely plant a model. We could actually throw the entire machine learning book at a particular model, but if your data's crap, it's not going to do any good. Basically, your model's still going to underperform, and it'll be a waste of time. Okay, so another point worth mentioning, that this particular model that we've augmented achieves a slightly lower evaluation accuracy when compared to the model without data augmentation. And that is because this particular model needs more epochs to train. So if you're training your own model, increase the epochs and you'll see a much better, you know, evaluation accuracy. If you want to check this issue, just check back to the previous model that we used on the full data set. And the training accuracy reached almost 100%, where the augmented ones can still do some improvement, really. So, yeah. And that is pretty much it. So, it's quite interesting to see how data alone can impact a deep learning model. And hopefully this helped you have a better understanding, of the importance of raw data that you're inputting a model. What we've done here is basically figured out ways to diagnose the effects of a class imbalance and look at specific metrics to spot this problem. Adding more data is a simple way to overcome class imbalance, but it's not really always feasible in real life. And then but to overcome this, what we've done is applied multiple geometric transformations to the images in the training data set, and that has allowed us to generate an augmented version. And this has allowed to reduce overfitting. Changing the network architecture is an alternative method to reduce overfitting, but I wanted to show you how to do it through data. In practice, it's a good idea to implement both. So experiment with it, and I'll see you next time.